All right, so um, an arbitrary discrete distribution, this ON method is actually fast if you're going to generate a few numbers, which just generate a single uniform random number and look which interval it belongs to. You can also do an O log n method by searching these intervals by using binary search. That's also an efficient way to do that, right? I mean, you can generate a uniform random number and start with the middle and see where it falls in by doing binary search. This O1 method, which is called the alias method, it's also known as the Robin Hood method, first preprocesses the set of intervals in such a way that um, here, let me just try to quickly talk about the idea behind that algorithm. If you have n numbers, if your uniform random number takes n different values, if this was uniform, if they were all uniformly distributed, they would all be at the same length of, I mean here, 1 over n. They will all have 1 over n probabilities, right? If they were all equal. So if in a system where all variables have equal values, it will be 1 over n. But since it's an arbitrary discrete distribution, some of them have larger values, which means that some of them have to have smaller values. Okay, you cannot have one large and the others remaining the same, because it's not called a zero-sum game, but this is like a one-sum game, or this probabilities, they have to add up to a total of 1. So if one gets larger, the other gets smaller. So you will have a bunch of such things, some small probabilities that are around, and some large probabilities that are around. Okay. So the idea is preprocess these probabilities in such a way that you take the part that is above 1 over n. Okay, you take this one. Let's see if I'll be able to do that here. You take this one and you put it here to the ones that are smaller. Okay, now the algorithm, so but how do you ensure that at the end all of them are, that's why it's called the Robin Hood method. But the idea is this, there's some mathematical proof part of this one that shows that you can make this distribution from larger ones to smaller ones in such a way that at every bin, I'm sorry, not this, at every bin here, there will be exactly two different values. I mean, uh, you're not going to put lots of large parts from multiple ones to fill this thing. Even this is a small thing. The mathematical proof shows you that there should be one large enough which has to fill in this gap, and you get that one from that part to fill in this gap. So in every interval, there will be two parts, saying that, for example, with this probability, you generate a, for example, value n minus 1, that's just next to that. And with this probability, you will be generating, I mean, if you look at this 1 over n, that 1 over n part, it's divided into this other part. Sorry, let's select this one. If this was, for example, n minus 4 here, this part will belong to n minus 4, this part will belong to n minus 1. So this theorem says that it's always possible to rearrange all these large probabilities, small probabilities, such that in every bin there will be at most two values like this. Some of them may still have one value like this, and each of them at the end will be equal. So that's why it's called the Robin Hood method, or maybe you could have called the communism method, which makes everybody equal by taking from the rich, giving it to the poor, so everyone is equal. But it's called the alias method. I don't know why it's called that, but what happens is that if at every bin we have two values, The good thing there, all 1 over n, is that all you need to do is generate 2 uniform random values. So that's why it's in O1. So you generate first uniform random number. You just, with that uniform random number, since each of them is one, all the intervals are equal size, 1 over n, 1 over n. With O1 time, with this single, for example, if you generate 0.36, if you know that you have 10 values, you immediately know that it's in the fourth bin. Okay, since because each bin is 0.1 length, if they're uniform length, the good thing about uniform length is that when you generate a uniform random number with just a simple single mathematical formula, you would find that it falls in this range. So in O1 time, you first find which range it falls to. You generate a second uniform random variable to figure out which only has a single interval boundary. You generate another uniform random number. If that uniform random number falls into this area, with O1 time again, you can find whether it falls in this area, in this area. If it falls in this area, you generate this number as your random variable, otherwise this. So this is a really nice technique in O1 time. Of course, it will work only after this pre-processing of these bins into this equal length ones. So this part is time consuming, which probably requires at least O(n) time. I think there may be an n log n or n square algorithm to rearrange your discrete probabilities to make them equal like this, but that's one time cost. After you have your discrete distribution arranged like this in O1 time, you would be able to sample from this arbitrary discrete distribution very efficiently. Okay, so that's the Elias method, which is not in the book. I just wanted to tell you that such a thing can come up as an interview question if you're going to interview at Google, Microsoft, or some other company when you graduate. Okay, so and this algorithm in the book, on the other hand, is an O(n) time algorithm in the worst case. For any distribution, it generates a single random number, and then it tries to find which interval it belongs to by iteratively looking at intervals from the beginning until it finds where it falls. So in the worst case, it's going to go over all the intervals, finding which it falls into. The problem here was, again, the lengths of the intervals are not uniform. They are not same length intervals, so you cannot if you have arbitrary length intervals, you cannot just find which interval a number falls into by hashing or in O1 time by some mathematical function, because they're of different lengths. There are data structures like segment trees or interval trees, but they will give you O log n time finding which interval a point belongs to. The simplest algorithm that is in the book that takes O(n) time, linear time, to, in the worst case, to find where this uniform number belongs to which interval. Okay, so this step 3 needs you to go over each interval one by one. So it's in O(n) time. So if your random variable takes n times, it will on the average take O(n) time. So this one is the O1 method. So similar to this general method, there's an algorithm in the book to generate Poisson random variables. Although Poisson goes all the way to infinity, again, its range is not, finite. It gets values from 0 to all the way to infinity. Okay, so if you remember what Poisson was, it was about the exponential was waiting times. It was the number of accidents that happen or number of events that happen. I said accidents because it's always the same example that we talk about, the number of accidents in a day. So it's actually the number of events, number of random events that happen in a fixed interval. So you may get 0 events, 1 event, 2 events, or infinitely many events. But the probability to get infinitely many events in that interval is really, really small. Therefore, and it diminishes after a certain time. So in the book, we have this algorithm which starts with the first probability 0. You generate a single random number. If it falls into the CDF of where x is equal to 0, okay, you generate that 0 as your Poisson variable. If not, you by using the CDF function, you see whether this generated U falls into the region that belongs to Poisson x is equal to 1. If not, you keep increasing that. And at some point, this, after, for example, x becomes after, for example, after I is equal to 15, this CDF becomes very close to 1, and which means that your generated random variable is going to most probably be in that interval anyway. You want the probability to go, the probability that this loop runs all the way to infinity is very small. Okay, so if you look at this function, what we do is, this is e to the minus lambda. So if you look at this function, e to the minus lambda, lambda to the power I, divided by gamma I plus 1, this is the CDF formula for, or is it this? No, this is actually the PDF, I think, because we keep adding this. So this is the PDF, not the CDF. So for a given I, this is the probability mass function for x, the probability that x is equal to I for a Poisson variable, and the only parameter that you can see here is the lambda. So given some lambda, for example, this is lambda is equal, the equality is forgotten here, so there's a typo. Lambda is equal to 5. For lambda is equal to 5, what number we are going to generate? Let's see. Let's try to run this code on Octave Online. Also, I want to take a note of a typo in the book about this code. This is the corrected code that you see on the slide. In the book, there is a bug actually in this code, in which this I is equal to I plus 1 is written, the order of these statements are different, which will make the program run incorrectly. It's going to actually execute the PMF function for F0 twice. So this is what I mean. Let's go to that PMF part in the book. Sorry, the Poisson random number generation. So it's this one. So this is the code. It's the same code that I have on my slides. The only difference is that this I is equal to I plus 1 changes. The order is changed in this while loop. So let's take a look at this code and let's try to understand what it's doing. So this is the PMF. As you can see, the probability that the Poisson random variable x is equal to xi is given to us as e to the minus lambda, lambda to the power I divided by I factorial. Actually, we could have this is the I factorial, which is equal to, if this I is a discrete number, if it's an integer, we know that this gamma function directly gives the factorial. It gives the factorial of whatever you put here minus 1. So this gamma I plus 1 is the factorial I function. But I think in MATLAB, the factorial function doesn't exist as this. That's why they use gamma function here. Okay, so another note here. This gamma I plus 1 is the same as factorial I, which is the same thing in this formula. So this is our PMF, the probability that Poisson is equal to some number. So what we do is we generate this cumulative distribution function by adding ourselves PMFs one by one. So we generate a uniform random number. We generate this only once for a single Poisson random number. We generate one uniform random number. And the next step will be to figure out which interval this U belongs to. If it's less than P0, it means that P0 was successful. It's in the interval between 0 to P0, and we are going to generate the value of 0 for this value. So that's why I is the value that we are going to generate for this Poisson random variable. So we initialize it to 0. If we don't enter into this, and this f is equal to e to the minus lambda is when you put 0 in terms of for I here, it's going to be 1 over 1 e to the minus lambda. So e to the minus lambda is the probability that lambda is equal, x is equal to 0 for any given Poisson variable. So if our u variable that we generated is less than that, it means that we can generate this value of 0 for that Poisson variable. And that's exactly what we do. If u is less than this computed f, if it means that it's in that very first interval. So we don't go into this while loop. We end and we just say x is equal to 0. That's our x's. Here, the generated random variable that we will be using beyond this point, however we are going to use it. But you see the problem here. If it's not in the first interval, we go into the loop, and the loop has to add, it has to find p0 plus p1 to find the end of the second interval. So this f function, f here, is a value that shows the end of the intervals for each iteration of those bins. So here the f is actually keeping track of this at every iteration. The first initial value of f here, as you can see, is the probability that x, that Poisson variable, is equal to 0. So if it's equal to 0, we just return this. Now, I keep incrementing f by adding the PMF of the next value. So in Poisson, it was 0, 1, 2, so it has to go like this. So I need to add the PMF of 1 to f in order to find the next boundary. The following boundary will be found by adding PMF of 2, the following PMF of 3, like that. So I need to add to f now the PMF of 1, but at this point I is equal to 0, right? So I is still 0, and this function is put there assuming that I is already incremented, so which was wrong. So that's the bug in the book's code. This I is equal to I plus 1 have to be put before this code. Then we update our boundary and check the generated u against that next boundary. If it's still larger than that, we keep incrementing. We keep looking at the next interval, next interval, next interval. And as soon as u is less than the next interval boundary f, we quit, and whatever I is in that, whatever I is, it shows our interval number starting at 0, of course, and we report that as our Poisson random variable. So this is the last thing I'm going to talk about, discrete random variable generation. And now we're going to go to continuous random variable generation. So we have now by using uniform random numbers, we know how to simulate any discrete distribution. So that's really a good thing to know. Now the only thing that's left is if in our simulation we also have continuous random variables. How do we simulate them? For example, imagine you have, not this one. Yeah, let's get a new whiteboard here. Imagine you want to develop a game in which you're going to have some enemies as enemy avatars that you want to put inside your game. Usually in a game, what happens is that the avatars are modeled previously and their sizes. For example, the enemies will have all same height. They are all 180 centimeters. But in real life, not everybody is 180 centimeters. That's actually some unnatural part of being in a game. Everything is standard. Now imagine you want to put some realism into your first-person shooter game in which some of the enemies are going to be short, some of them are going to be taller, and it's easy to do that by just using scaling those models. You can scale your model to have, for example, 180 centimeters on the average, but you want some of the enemies go as high as 2 meters, and some enemies may be short, 160 centimeters. If you ask this problem to an intern in a game company to say that, okay, we want to randomize this, give us some enemy heights between 160 centimeters and 200 centimeters, and we want our enemies to have some random heights within this interval. if that person did not take this statistics course, what do you think that intern is going to do? Just use the rand function available in C or Python or C sharp. If that person is programming in Unity, probably they're using C sharp. So what will happen is that, I mean, this would actually be what I would do if I was asked this before I started teaching this course. I would just say, okay, between 100 and 200, I would just generate a random number and take its mode 40. Okay, add this to 160. Yeah, that's it. It will give you random numbers. It will give you random numbers between 160 and 200. Nicely, you can have, and you would test this program, and it will say, okay, you see, sometimes we get 170, sometimes we get 190, so that's randomized. Perfect. Or is it perfect? So because do we really have equal probability short people and equal probability 2-meter people in population? Is people height distributed uniformly like this? Do you think so? Probably not, right? It's probably something like this. Normally distributed, because heights, weights, things like that are normally distributed. Now, here's the problem then. How do you, if it's normally distributed, if I say that, if it's saying that, okay, the average height is, mu is 180 with a 180 centimeter with a standard deviation of 3 centimeters. If I tell you this, can you generate random numbers from this distribution for your game, in which seeing an enemy avatar 2 meters will be really unlikely, or seeing a very short avatar is also going to be very unlikely. So this is normal distribution. How can you use your rand function, which gives you uniform numbers, but sample something which is from normal distribution, which will look a lot more realistic than this implementation of uniform random numbers between 160 and 200 meters. Okay, so this is what I mean. This section itself is going to be really helpful to sample from continuous distribution. You will be able to sample from a distribution that is like this, normally distributed, if you know, for example, the inverse transform method. Inverse transform method, the first thing we are going to learn, which is if somebody gives you the inverse CDF, if we have the inverse CDF of normal, do we have that in MATLAB? Let's see. MATLAB inverse CDF normal. Yeah, actually I have queried this before. Norm in P and mu. So let's see what it is. And it says sigma, standard deviation. So we give a probability, mu, sigma. So this is the inverse CDF. Okay. Now, before going into the book's details, so I can use this function. Now, here's the magic that works. Actually, you don't. With this inverse transform method, it says that the inverse of any cumulative distribution function is standard uniform. This is a really strong theorem. Look at this. Any random variable, you have its CDF for any random variable. The inverse of the inverse function, though, so inverse of CDF means that instead of, so when you say CDF x, it gives you a probability, right? CDF of x is some value between 0 and 1. CDF of any x, any distribution, coming from any distribution. If you call the CDF function, it's cumulative distribution function, we know that it's going to give you the probability that x is less than 4. So if you give a particular x, is the probability that the random variable is less than or equal to this x, and this u will always be between 0 and 1. Now, here's the interesting thing. The theorem, this strong theorem, says that this u, independent of what this x's distribution is, this U is always standard uniform. Okay, so that's something very interesting, which means that if you have the inverse function of that CDF, you give it a standard uniform random number, what is it going to give you? It's going to give you X, which will be distributed in the distribution that you're looking for. So what it means is that I can use that norm in function with a uniform number, this P. So let's try that here on our Octave Online. Click here to reconnect. Do I need to load the package again? Just to make sure. Let's do that. Statistics. Yeah. Now, norm inverse. Take a uniform random number, mu, 180 centimeters with a standard deviation of 3. That's your normal random number. Do it again. Look at this. They're close to 180. And what do you think these numbers are that we get in the answer? They are normally distributed with mu is equal to 180 and standard deviation 3. Okay. Now, if you just plot the histogram of these many random numbers, they will not be between 160 and 200 meters. If you want to have more range, more variation in your enemy avatar's height, let's increase the standard deviation to 10. Let's see what happens. Now you get small values and large values, but if you do this simulation on the long run, what you will see is that the average is at 180 centimeters and the standard deviation is 10. Okay, so look at this. By using this theorem of saying that the CDF, inverse CDF of any function, any random variable is standard uniform, we were able to give that standard uniform random variable to as input to our inverse function with these parameters, of course, to get ourselves. And normally we were able to generate normally distributed random numbers. So normal distribution is nice. It's inverse function. Inverse CDF is already given in MATLAB, so it's good. You can use this if you want to generate from normal distribution. You can directly use this function. And not all functions are nicely invertible like this, but if you have a function that you can invert, it will work. Now, what is the intuition behind this theorem? So look at this theorem too. So it was, let x be a continuous random variable with some CDF arbitrary. Define a random variable u is equal to fx. So the distribution of u is uniform 0, 1. So this is the mathematical proof of this theorem. And the intuition, I just want to show, instead of the mathematical proof, I want to show you the intuition behind why it is uniform. Think about the CDF of some value. Actually, there's a really nice figure on Wikipedia. I'm going to also show you that. But first, I want to show you a CDF of some x. So let x be the random variable in some range. So the x-axis show us our domain. What will happen is that whatever x is, x may start at 3, it may go all the way to something, but let's this y-axis be put at where x started. So the CDF is going to be a non-decreasing function, something like this. Okay, or it may, let me draw some another CDF that looks a little bit different. Look at this. And here, let's have this one at 1.0. Here is 0.0. And these are the values of x that we can take, maybe from 0 to 200, maybe. I don't know. I mean, this x-axis is not necessarily between 0 and 1. It can be, it's the domain, these are the values that x can take. Now, Let's look at the CDF. What do you think is going on here in these steep regions? So let's try to understand what the CDF is intuitively. For example, let's take a look at from here to here. What does it tell us? For example, if this is 100 and this is 110, the probability. So if you think about the PDF from here, what we will have here is that we will have a peak. The PDF of this is going to, the PDF of X is going to look something like this, where this peak is between 100 and 110. What it tells you that the probability, the CDF function, increases rapidly when you go from 100 and 110, which means that the probability, for example, if you look at the Y values, if I ask you this, so this is the value of 110, this is the value of 100. If I ask you what is the probability that X is between 100 and 110, okay? What is this probability? It's CDF of this, CDF of 110 minus CDF of 100, right? So this region here will be that probability. And since the increase was really quick, what happened was the difference between in the y-axis was large because of that. But this is a really small interval compared to 0 to 200. Only in 10 values we get this large probability. Now, what is interesting here is that if you just imagine, now here is the critical thing. Imagine we get random points in equal intervals. This one, I want to get different colors here. This one, let's make it blue. Actually, instead of drawing this, I can directly show you the Wikipedia article too, but look at this. I'm getting equal intervals, like as a uniform random number would behave. Now, look at these uniform numbers here. If you have the inverse CDF, so this is the CDF of X, the inverse of the inverse of the CDF function is like this. This will be your x-axis, and you will be generating these things. So, for example, if you whatever value you have here, these tick marks, if you give these tick marks to the inverse function, okay, let's call these tick marks u. If you give them to u, what is going to give you as a result? It's going to give you a value that is here. It's going to give you this. This is inverse CDF is going to, this will be your y-axis in that inverse CDF. Just try to look at sideways. Now you see what happened are uniform random variables between this interval and this interval, which was equal amount. I mean, they were all equally spaced. Now, what happens if you map them with this CDF function? They all fall into this very small region between 100 and 10. So if the probability to observe something is large between small intervals, these equally spaced things, which are uniformly distributed, they your CDF function, since it was increasing rapidly, it arranges them into this small region, which means that the probability to observe them is small. So that's the intuition behind why CDF of X is uniform. And its mathematical proof is in the book and on the slides with a little bit more description. But this is the idea, and I think I was able to replicate the figure in the Wikipedia article. Not bad. So let me show you this. So this is in Wikipedia. It's showing the exponential distribution, how the PDF or the CDF of exponential distribution works, and it gets these equal sized points from y-axis. So this is the CDF. And when you look at how they fall onto these, you see between 1 over lambda and this, you get large values. The separation is like this. They are non-uniformly distributed. All right, so this was the exponential. The exponential distribution, its inverse CDF is also easy to compute. So you can also use this function that you see here. And if you generate as y0, if you generate uniform random numbers, plug in here, x zeros will be exponentially distributed with some lambda. So that's really uniform. This inverse uniform method is really works like magic. In all one time, you're able to sample from continuous distributions if you know their inverse CDF function. And now let's go to the slides. Okay, so it's also called the inverse transform method. The proof follows from try to figure that the CDF of uniform distribution itself is equal to U. Okay, so this, if you remember the PDF of standard uniform. Oh yeah, exactly. So when we are doing this sorry, let me read the question first. So Furkan is asking, when we are doing the norm in rand mu sigma, is rand r uniform color points on y-axis here? Exactly. So when we take when we run that rand function gives us uniformly distributed values between 0 and 1. Since the y-axis in CDF is between 0 and 1, we generate uniformly random numbers between 0 and 1. Those are the color points on the y-axis. And when you, so this is what you see here is not f minus x, f inverse x. This is the fx. So if you have f inverse x, what you would do is these will be your x-axis. You give them to your inverse x. They will give you these values. That norm inverse does exactly that. You give this rand values, the uniform values, as parameters to your inverse function, and they will generate you the x. And those x's will be normally distributed. If you use norm in, I wonder whether we have exp_inv. There may be. So let's see. Exp_inv. Is there such a function? Yeah, there is. X lambda. So rand 5. This is a random number that is exponentially distributed with lambda is equal to 5. Very convenient, right? I mean, because the inverse function, you give uniform random numbers. All these rand, they are uniform, standard uniform random numbers. But if you put them in your inverse CDF as a parameter, it will give you, as you can see there, these values here are exponential random numbers, continuous exponential random numbers, in which so this is like the average waiting time. Exponential variables are waiting times, 6.2 minutes, 2.3 minutes. So if the average waiting time for the next bus is 5 minutes, generate me random waiting times for the next bus. So this will be really good also if you're, again, in a game. If you're, for example, try to simulate the time until the next enemy comes. So depending on the difficulty level you have chosen, you may have each of these lambdas may correspond to different difficulty levels. The time until next enemy, 1 minute or 1 second. If time until next enemy is 1 second, just try to simulate that. Instead of just getting enemies every 1 second, such a game will be really boring, right? I mean, you will be facing enemies every 1 second. It will be really regular. We don't want regularities in our natural lives. So it should look, even if it's a game, it should look simulated, random. And if the average waiting time is 1 second, here we can just use this function to generate different number of seconds waiting time until the next enemy comes. For a less difficulty level, medium difficulty, every enemy and one enemy every 5 seconds, you generate random numbers like this. Well, it was very quick in certain cases, but look at this, they're random. Even if it's medium difficulty, we can get, you may sometimes wait 5.6 seconds until the next enemy, sometimes 1.1 seconds, sometimes 0.5 seconds, sometimes 8.7 seconds. So these are random numbers coming from exponential distribution where average waiting time is 5 minutes. Wow, look at this 25. It's really low probability to receive 25, but we got that. Sometimes we get 25, sometimes we get 0.02. Both of them are low probabilities, but they're non-zero probabilities. If you just do this a lot, their average will be 5. Average waiting time will be 5. So that's the inverse transform method. We take the inverse function of the CDF, we generate a uniform random number and give it as an input to this inverse transform, plug it in, and it gives us a random number from that distribution. This is that exponential. And in exponential distribution, there's another thing. For example, in the formula, we get here in the inverse CDF formula, we get 1 minus u as a parameter. Instead of taking 1 minus u all the time, we can also use u, because u and 1 minus u, they're all both uniformly distributed. They're all standard uniform. If you generate a random number u, if you take 1 minus u, it will also be a standard uniform random number. So therefore, instead of 1 minus u here, you can also use u. Sometimes why don't we always use, so this is such a magical nice method, why don't we use it all the time? Because for certain distributions, taking the inverse function may be difficult. The CDF may not be very easy to compute. But as we have just seen, here in MATLAB, we have, if you want to sample from exponential distribution or normal distribution, it's just one line of code. Okay, so the inverse CDF of exponential or normal distribution, it's really easy. So we can do that. But for the inverse transform may not be applicable for all of the continuous distributions. For example, we cannot use it for discrete distributions. Actually, we're talking this method under the name of continuous distributions, but it may be also applicable to discrete distributions if it's such a magical method, but it doesn't, because discrete distributions they don't have continuous CDFs. The inverse CDF sometimes may not exist. It may have no roots, as u is continuous here. Therefore, there's a method that applies that, which is very similar to, which is exactly what we have done actually for looking at intervals. But we generated a u, we tried to figure out which interval it belonged to. Actually, what we were doing, that we were finding the interval and our uniform number past the minimum number in which our uniform number is larger than that CDF. Okay, so this is exact same method. So what this saying is minimum x such that fx, the cumulative distribution function, is greater than u. This is exactly what we did in that while loop. Remember when we were generating that Poisson random variable? We generated a u and we tried to figure out the endpoint where u was less than that endpoint. That the minimum that by doing that gives, and then we generated that x for that. This is that same method we have used. There's an example on geometric variables which is discrete. We can actually use this since geometric variables. The thing is that in Poisson we did not use the inverse formula, but we keep adding these f functions. But if we have the f minus x, the inverse of f directly available, and this is the case for geometric variable, you can generate a geometric variable in all one time by just plugging in your random variable, uniform random variable, into this equation. This is the ceiling of, and then 1 minus u. Again, you may replace 1 minus u with u here, divided by ln 1 minus p. This will be your geometric, again with one equation in u one time, instead of checking each loop one by one, because the inverse function is available to you and the minimum will be given by the ceiling formula. The geometric variable will be the ceiling of this exponent. Also, the relationship, use the relationship between exponential and geometric variable, but you can also use this formula to do that. For your last fourth assignment, you will be able to use all the formulas and the code that is available in the book. You may also use MATLAB, Octave Online functions for to simulate these random variables. But we will also have some part in your fourth assignment in which we will need to generate random variables from some arbitrary probability density function. And you may use the inverse CDF by taking the they will be maybe invertible, but we will see another method next, which is called the rejection method. But I will continue with the rejection method on Tuesday. So we will still use one additional R on this chapter. Because we will have plenty of time for our last chapter, chapter 6, which is stochastic variables, or we will see time series random variables in the last chapter that we are going to cover this semester, chapter 6. But we can spare 1 hour from those 2 weeks for this chapter 5. So I'm going to continue with the rejection method on Tuesday. And we will be able to generate random variables from arbitrary distributions with really arbitrary looking CDF, PDFs like this, for example. How do you generate? Look at this function. It may be a very complicated function, maybe a partial function. This may be the PDF. Sorry, let me write PDF x here, and this is x. Given an x, the PDF may be like this. How do you simulate random numbers from this arbitrary distribution? Okay, in this case, inverse transform may not be really applicable. And we will see this method I mentioned last Tuesday, in which we are going to generate uniform random numbers within this rectangle and just give random numbers which are under this curve of PDF. That will be the rejection sampling method that we will use, and we will see one example, and after that I will show you an example about Monte Carlo methods, and which you will also experience on your last assignment. So that's it from me for today. I will be happy to answer your questions if you have any. Let me stop recording.